Okay, so we're going to go over exam number 2, version A, work through the solutions. First question we have is a balancing question. So we have NO2 gas plus H2O liquid water, and that goes to form HNO3, which is nitric acid, and then NO, nitrogen monoxide. So again, we can count these up. What do we have here? We've got nitrogens, oxygens, and hydrogens. I don't think we have any other elements. If I count all the ones on the reactant side, we're going to have 1 nitrogen, 2 over here. We'll have 1, 2, 3 oxygens on the left, 1, 2, 3, 4 on the right, and 1, 2 hydrogens on the left and 1 on the right. So you can see none of these balance right now, nitrogens, hydrogens, or oxygens. So we put a 3 in front of our NO2 here. That's going to, let's see, give us now 3 nitrogens on the left and 1, and then there's 2 oxygens per NO2, so 3 times 2 is 6, plus the 1 from the water. We'll change that to 7, and then our hydrogens will stay at 2. Let's try to put, so nothing's balanced yet. Let's put a 2 in front of our HNO3. If we do that, there's 1 hydrogen per nitric acid. If we put a 2 in front of that, it's going to change that to 2. Now we're going to have 2 times the 3 oxygens is 6, plus the 1 in the NO is going to give us 7 of those. And then 1, 2 nitrogens in there, plus the other 1 in the NO should be 3 of those. So now they match. 3 nitrogens on each side, 7 oxygens on each side, 2 hydrogens on each side. So our coefficients here, we've got a 3, a 1, a 2, and a 1. So that should have been 3, 1, 2, 1, or answer B. Oh, shoot. There's that. Next one now, we have moles of nitrogen. So we have 58.6 grams of potassium nitrate, and its molar mass is 101.11 grams per mole. We have this balanced reaction equation. Decomposes and gives us that right there. So we want to know how many moles of nitrogen, the N2 here, are we going to get if we decompose this much potassium nitrate? So we need to find out how many moles of potassium nitrate we have. So we're going to take our 58.1 grams and we're going to divide that by the molar mass. Gives us 0.57957 moles of KNO3. And then we're going to utilize the ratio from the balanced equation. So there's 2 N2s for every 4 potassium nitrates, or 1 to 2. Multiply that by how many moles of potassium nitrate we have. And the potassium nitrate there will cancel, and we'll end up with N2. So that's 0.28 or 28978 or 0.290 moles. Answer A. Next, we'll look at which of the following signs on Q and W represent a system that's having work done upon it by the surroundings, as well as losing heat to the surroundings. So Q is our heat term. If it's losing heat, then it should have a negative sign. So that right there is either going to be answer A or B. And it's having work done upon it by the surroundings. So the surroundings are doing work on it, putting energy into it. So the work term, the W term there should be positive. So that should be answer A right there. All right. Now we have another limiting reactant problem now. All right, so we've got our balanced equation. N2O4 plus 2N2H4 goes to make 3N2 and 4H2O. We have a 70 grams starting with of the N2O4 and 45 grams of the N2H4, and we need to find out how much nitrogen gas can we be formed. So how much of this are we going to make? We need to find out of these two, which one is the limiting reactant. So we're going to start with the N2O4. We'll find out how many moles of that do we have. So we're going to divide by the molar mass. Should be about 92, right? 64 plus 28. About 92 grams. That'll get us to moles of N2O4. And then if we multiply that by the ratio of N2 to N2O4, it'll show us how many moles of the N2 we would end up making if we used up all of this. And that is 2.283 moles of N2. We're going to do the same thing with the N2O4. Now we have 45 grams of that divided by its molar mass, which would be 32, and then multiplied by its ratio to that same product, the N2, the one we're interested in, although now it is a 3-to-2 ratio, and that's going to give us 2.109 moles of N2. So the one that produces the least amount of product is our limiting reactant. That's the N2O4. And so then we're going to utilize now knowing how many moles of that we would make, or that's our theoretical yield. And we wanted that actually knowing grams. Yep, so we're going to multiply that by the molar mass of N2. There's two nitrogens, so 1 plus another, 14 plus 14 is 28. And that gets us to the 59 grams of N2, or answer B. Question 5. This is calculated as the ratio of the actual yield to the theoretical yield, or if we put the actual yield over the theoretical yield, that will give us our percent yield. Identify the combustion reaction. Combustion is reacting something with O2 and producing some oxygen-containing product, typically at least water, maybe something else, and you'll note for all of these, they're all reacting with O2, and they're all producing oxygen-containing products. So they are all combustion reactions. Answer D. All right, to make 1 liter of a 0.25 molar KCl solution, how much KCl would we need? So, or potassium chloride. So it's a 0.25 molar. So we can take our 0.25 capital M and we could rewrite that as moles of KCl per liter of solution. And if we multiply that by how many liters we have, which is 1, we'll see that what we would need are 0.250 moles of that potassium chloride. So if we can find the mass of potassium and the mass of chloride, or that should be about 39.1 plus 35.45. Times 0.25 gives us 18.6 grams, or answer B. All right, particular alloy has composition of 3 metals. It's 65% copper, 33% zinc, and 2% tin. Which of the following would be considered the solute? So again, it's a mixture. The majority component is the solvent, and the minority component or components are the solutes. So both tin and zinc are the minority components in this case. They would be the solutes, and the copper would be the solvent. All right, dilution problem. Why is that not? What are you doing? It's not displaying the screen for some reason. Let's try again. There we go. All right, so we have to dilute a concentrated solution, or something with a higher concentration. That's the 3.5 molar Heaps buffer. We have 125 milliliters of that, and we want to dilute that to 900 milliliters. And then we want to know what's the new concentration when we do that. So we're going to use our dilution equation. M1V1 equals M2V2. So our M1, our high concentrations of 3.5 times our volume, 120, sorry, that's in milliliters. We could convert that to liters. We can leave it in milliliters. It won't matter. Whatever units we have it in, that's going to be what volume we should see on the other side. We don't know our M2. We do know our V2. We'll keep that in milliliters as well. So if I divide both sides by that 900 milliliters, then I'll have my concentration here in molarity, which should be 0.486 molar, or A. Should be lower, noticeably lower than what we started with. Our volume's about, 7 times as much. So it makes sense that we'd have about 1/7 the concentration there. Question 10, identify HBr as an electrolyte. So what is HBr? It's aqueous, it's dissolved in water. This is one of our 6 strong acids. And you remember, any strong acids will dissociate completely. They are strong electrolytes. So if I put 100 HBr molecules in water, I get 100 H pluses and 100 Br minuses. Identify the spectator ions in the following equation. So I'm looking at the reactants. Everything is aqueous. Everything's dissolved and dissociated into its component ions. And then I go ahead and look at the product side, and I see that on the product side, we do have a precipitate. We have a solid, iron sulfide. So the two things that went into making that, the iron and the sulfur, they're not spectator ions. They changed from one side to the other. But the things that went into the sodium nitrate, or the things that were unchanged, like I said, are the sodium and the nitrate. We've got Na plus aqueous on the reactant side and Na plus aqueous on the product side, and NO3 minus aqueous on the reactant side, and it is identical on the product side. So those are our spectator ions, B. All right, titration question. So we've got, we're reacting sulfuric acid with potassium hydroxide. The H plus and the sulfuric acid are going to react with the OH minus and the KOH. So we're reacting an acid with a base. We're going to get HOH, or water, H2O. We're going to get some salt. The positive part is going to come from the base, from the potassium hydroxide, which is going to be the potassium. It has a +1 charge. And the anion is going to come from the acid, that's the SO4, the sulfate. The sulfate has a 2- charge. Potassium has a +1, so we're going to need 2 potassiums to balance out that sulfate. So I'm probably going to put a 2 in front of that. That's going to give me my 2 potassiums. And if sulfuric acid is polyprotic, it's got 2 acidic hydrogens. That means each one of those acidic hydrogens is going to need an OH to react with. We have 2 of them there, but 2 H pluses with 2 OH minuses will give us 2 waters. So we have a 1:2 ratio for our acid to our base. That's important. Now, we were given the volume and the concentration of the acid, so that should be enough information to determine liters. We have 50 milliliters, or 0.05 liters of that acid. We know its concentration, which is 0.1 moles per liter. So if I multiply the concentration by the volume, I will get the moles of H2SO4. And now that we know the balanced acid-base reaction, I can convert moles of the H2SO4 into moles of our titrant, the KOH, the potassium hydroxide. And that's a 2:1 ratio, so we should have double the number of moles of potassium hydroxide. 0.01, and the last thing they wanted, or what we really want to find at the very end, is then what volume of this do we need? So if we know how many moles of it we're going to need, and we know the concentration of the potassium hydroxide, then we can divide by the concentration, which is 0.15 molar. Moles will cancel, and we'll be left with liters. (66.6 milliliters in this case, or answer D. All right, use the information provided to solve the following delta H for the reaction. So I've got SO2 Cl2 plus 2H2O goes to form 2HCl plus H2SO4. We want to find the delta H. We're given the enthalpy formations of all the reactants and products. And so in this case, we're going to do products minus reactants. So we'll start with the HCl. We have 2 of those, so we're going to take 2 times -92. And then we have one more product, H2SO4. We only have 1 of those, so we'll multiply that -814 by 1. And then from those, subtract our reactants. 1 times the negative 364 for the SO2Cl2. And then we have 2 of those waters, so we're going to multiply the negative 286 by 2. And we should get negative 62 kilojoules, or answer C. From the oxidation state of phosphorus in PO2, 3 minus. So we've got a polyatomic ion here. We've got all nonmetals. I know that the oxidation state of all my nonmetals has to add up to the charge for this polyatomic ion, which is -3. Oxygens are higher on the table of nonmetals, fluorine, hydrogen, oxygen, and then a ways to go to get to the phosphorus. So since they're above it, they're going to have a oxidation state of -2. You can see here the phosphorus should be a +1. Answer C. Which element is undergoing oxidation in the following reaction? So I've got solid zinc plus silver nitrate, aqueous, that goes to form zinc 2 nitrate, aqueous, and solid silver. So assign an oxidation state to every atom present here. Zinc, it's a free element in its naturally occurring state. It will have an oxidation state of 0. Nitrate has an overall oxidation state of -1. Each oxygen would be a -2, and then the nitrogen would be a +5. Now, this starts as nitrate and ends as nitrate. So if we came over to this nitrate, we would find the same oxidation states of everything in there. If we have the polyatomic ion that doesn't change at all, exact same atoms, exact same number of atoms, exact same charge, the oxidation states on those individual atoms wouldn't change, so we wouldn't necessarily have to do anything with that. And then the silvers, each of the silvers in here would be +1. Going over here now zinc is part of this ionic compound. It's the cation, it's now charged, and it's got a +2 charge, so whatever its charge is, that's going to be its oxidation state. And silver now is our element in its free element in its naturally occurring form. So it's going to have an oxidation state of 0. So you can see we want the one undergoing oxidation, the one that became more positive or less negative, the one that lost electrons, and that would be the zinc. Went from 0 to a +2, so it had to lose 2 electrons. And so that's zinc, answer C. All right, billiard ball rolls across the ground, losing 95 calories to friction, and then strikes another object. So our heat term would be -95 calories, and then it does 235 calories of work on another object. So our W term would be -235. So our change, or our delta E, is Q plus W, or -95 plus a -235. So that's -330 calories. And then we just have to go from calories to joules. The conversion factor is the same as the specific heat of water. So we'd have 4.8 joules per calorie. So we get -1,379 joules. round that, I guess, to 1380. Answer B. Determine the amount of energy lost when a gold nugget is thrown into a snowbank and cools. So we know what the substance is. We have a mass. We have a temperature change. We have a specific heat capacity. We want to find the energy lost as heat. So we're going to use the M equals, or Q equals MCAT, sorry. So our mass times our specific heat times our change in temperature. So our final temperature is 268. Our initial temperature is 298. So our change in temperature is 30 Kelvin. And our mass then, 276, it's already in grams, times our specific heat, 0.128 joules gram degrees Celsius. The scale for Celsius and Kelvin are the same. A 30-degree temperature change in Kelvin is the same as a 30-degree temperature change in Celsius. So keeping it in Kelvin or changing each of these to Celsius first wouldn't make any difference. And then we just multiply the whole thing through. And we get negative 1059.8 joules. Everything here is in kilojoules. So the amount of heat that's lost is 1.06 kilojoules. I have a negative sign indicating that it was lost. And then they already kind of indicate loss. So they just want to know what's the overall value of energy that was lost. 1.06 kilojoules. Answer B. An endothermic reaction so again, an endothermic reaction is going to absorb energy. So we should see a delta H that is positive. So right off the bat, that's either answer B or D. We can throw out A and C. And again, it's positive, meaning it's absorbing heat from the surroundings. It's taking in or it's increasing its internal energy. So that would be answer D. 19, we have that Hess's law problem here. So we need to look at what equation do we want to get to and what equations are we given. So we want to get to P4 plus 10Cl2 goes to form 4PCl5 phosphorus pentachloride. And we don't know the delta H for this. However, we are given this. And this. Okay, so I'm looking at some things here. I see the P4 in our second equation matches that. The Cl2 matches that. I like that. The PCl5 on our equation here is in the reactant side, but over here it's on the product side. As well as this chloride here doesn't really match. So I'm thinking maybe I want to flip that top reaction. And if I do that, it's going to give me this. Now, things are kind of on the right side, but I notice, the only place I see that PCl5, that phosphorus pentachloride is in that bottom reaction. And in the top reaction, I need 4 of those. So I think I'm going to multiply this whole thing through by 4. And if I do that, I have to multiply my delta H by 4. So I'm going to take negative 157 and multiply it by 4. And that's going to give me negative 628. Now let's see what we can or can't cancel here. Come on. There you go. All right. So I've got 4 PCl3s here on the reactant side there and the product side there. I think I can cancel those. I don't think anything else will cancel. So now I'm just going to add everything. I've got a single P4. I have 6 Cl2s here and 4 there. So together, they're on the same side of each reaction. They're going to combine into 10 Cl2s. And then I'm going to have my 4 PCl5 here. And again, this matches the final reaction I want to get to. So now, since I added those 2 reactions, I'm just going to add the delta H's. So I'm going to add negative 1,207 to negative 628. And I'm going to get a delta H of negative 1,835 kilojoules, or answer A. Then last reaction or question here. Here's our reaction. C6H6 plus 1502 gives us 12 CO2 and 6 H2O, and then the delta H for this reaction is negative 6,278 kilojoules. We told we have a specific mass of that that C6H6. We have 39.05 grams of that. And we're told we have excess oxygen, so we know the oxygens are excess reactant. So the C6H6 is our limiting reactant. So we need to find out how much energy or how much heat are we going to produce if we combust that much C6H6. So we have our balanced reaction equation. Everything's in molar ratios, essentially, is the stoichiometry. So I need to find out how many moles of that C6H6 do I have. So I'm going to take the 39.05 grams, and I'm going to divide by the molar mass, which should be about 78.07 grams. And that is 0.5002 moles. So we know how many moles of that C6H6 we have. Now we need to use the overall balanced equation and how much heat it evolves and relate the ratio. So what this reaction is telling us is for every 2 moles of that C6H6 we combust, we're going to get that much energy. So we're going to take the moles that we have. There we go. Times the amount of energy that we get for every 2 moles of that C6H6, and we should get 1,570 kilojoules of energy that comes out. So the amount of heat produced, 1,570 kilojoules of energy, or answer C. All right, that's everything. If you have any questions, please don't hesitate to ask. If you think there is an issue with your Scantron, please stop in. The average on this exam at the moment, although there's still some people that need to make it up, is a 60%, so lower than the first exam, but that's to be expected. The first exam deals with much easier material, much less math. If you still did well on this exam, that's great. That means your studies strategies are very good and accurate. If you definitely had a drop off, then look at how you're studying and maybe try to put in a little more effort. Make sure you're studying 6 days a week. Make sure you're working those end of chapter problems every single day. You reach out to me with any questions, and I'll see you in class in a little bit. Bye.